Hello everyone. So today we're going to continue on 8.4, and last video we get to talk about what we call flow line, which basically kind of show you the flow of a vector field by following all the vectors. And one of the important property that I mentioned to all of you is that when you try to draw the flow line, you notice that some flow line are moving away from each other, while some other, when in a certain part of the vector field, but in other part of the vector field, it seems like they will converge to each other. And that concept of, or that property of whether flow line diverges from each other, diverge from each other, or converge to each other is actually described by a property of the vector field called the divergence. Oops. So what does it mean by divergence of a vector field? A divergence of a vector field basically describe the following. Basically describe the tendency of a neighborhood around a single point to expand or contract based on the flow of the vector field. The tendency of a neighborhood around a point to expand or contract due to the flow of the vector field. Now, of course, it's extremely hard to actually see what a neighborhood is doing, but visually, we can identify this expansion or contraction by seeing how it affects flow line next to each other, and which is what divergence mean. When a neighborhood tend to expand, then the flow line would have the effect of moving away from each other, and that's what the word divergence would imply, meaning that flow line actually move away from each other. And when the neighborhood contract, then have the visual effect of forcing flow line to flow toward each other. And that would be when we say they're converging to a single point or converging together. So visually, you can see the neighborhood is expanding if flow lines are moving away from each other. And the neighborhood is contracting if flow lines are moving toward each other. So when they are expanding, they're moving away from each other, and that's what we refer to as they diverge. They diverge from each other. And when the neighborhood is contracting so that they move toward each other, we'll say that the flow line converges. They converge to each other. So therefore, you can basically see in this picture, you can identify that in this area, the neighborhood is actually expanding. That's the reason why all the flow line kind of spread out and move away from each other. Well, on this side, you can see that the flow line are contracting. So as I say, on this purple rectangle, the flow line actually diverge from each other. While on this side, they are converged to each other, toward each other. Now what we're going to try to do is try to create a numerical value that can describe this behavior. And this behavior will happen in every single point. And as a matter of fact, when you draw all the any flow line onto a vector field, the flow line would always be either contracting or expanding or staying the same distance from other flow line. So those are three different scenarios. Now, interesting thing about it is that we have the perfect way to describe this. And that is to use positive, negative, and 0 to define this. But the question is, how do we actually calculate this? So, show you how it's done. The divergence of a vector field F is called we will write this, is called div vector F. That stands for divergence of F. How do you calculate the divergence of a vector field F? This is how. The divergence of vector F is basically the sum of the main diagonal of the derivative matrix of F. So therefore, important to understand is that the divergence of a vector field is actually relating to its derivative matrix, which kind of makes sense because we are talking about how things contract or expand near a local area. And that changes is basically governed by the derivative, because the derivative allows you to change the value slightly. So basically what we want to know is that when you change the value slightly, is it going to move further away from the original point or moving kind of toward original points? Also important to note is the following. Because it's the sum of the main diagonal of the derivative matrix, which each of those are scalar, note that divergence of F is always a scalar. It cannot be anything else. So how do we actually define divergence? Let me show you. Definition. Let's say given a vector field F that map from Rn to Rn. And let's say that vector F of vector X is actually equal to F1 of vector X, F2 of vector X, to F sub n of vector X. Now, let's see if you remember what you have learned back in chapter 5. Each of these F sub 1, F sub 2, and F sub n, they are called coordinate function. By definition, they define one single coordinate within the vector function vector F. And they are all, because only give out one single value, they are all real value functions, which is the reason why there's no arrows on top of them. We're going to let this symbol, gradient symbol, be called the gradient operator. So what is the gradient operator? So that the gradient is basically equal to a vector that looks something like this. We basically ask you to partially differentiate over each of the independent variable. So now we can define what is the gradient, what is the divergence. The divergence of vector f is given by the formula div, divergence of vector f, is basically equal to the gradient operator dot product with vector f. And what does that mean? That would literally mean that we take this dx1, dx2, dot to dx sub n, dot product f1, f2, oops, f2, dot to fn. And so what does that mean? It means the following. It means that you apply d over dx1 to f1. So it becomes df1 over dx1. And then you apply d over dx2 to f2. And then df3 over dx3. And then this continue on until you get to the last one. That is what we call the divergence of f. Now, important to understand is that notes this is a function based on vector x. So therefore, to calculate the divergence of a vector field, you can basically form this formula, but to calculate the divergence at each individual point, you will have to plug in vector x. Now, maybe this is hard to understand, so maybe we look at one of the vector field that we know. Maybe we'll do this one right here. This one seems nice. And then we can try to calculate some different points on this graph and see how they, affect by the divergence. Okay, so let's go ahead and give it a try and see. So let's say we go let vector f of xy equal to x squared minus y squared minus 4 to xy. So how about let's find the divergence of the f. So remember, this would actually give us a function. Okay, so how do we go about doing that? Well, use the formula. div, divergence of f, is equal to df1 over dx1 plus df2 over dx2 plus plus dfn over dxn. For us, our function f only map from R2 to R2. So therefore, we only have to deal with two things. And also a good idea to identify f1 and f2 so that you can use the formula correctly. So based on the way the expression is written, f1 seems to be x squared minus y squared minus 4, and f2 seems to be 2xy. And for a 2 by 2 function that maps from R2 to R2, divergence of f would just simply equal to df1 over dx plus df2 over dy. Notice I dropped the x1, x2, and instead just use more common notation x and y instead, because that's what the variable we're using in this particular example. So that means I'm basically taking the derivative with respect to x of f1, which is x squared minus y squared minus 4, plus d over dy of 2xy. So that should be pretty simple. So if I take the derivative of the x squared minus y squared minus 4 in respect to x, what I get is 2x plus, and the derivative with respect to y of 2xy would be 2x also, and therefore become 4x. So it seems to me that our divergence of f is given to be the function 4x. Notice not actually dependent by the y value. That is actually quite interesting. Meaning that the divergence changes as you move from left to right, but the divergence doesn't change when you move up and down because it's independent of y value. Now, what does this function actually do? Okay, so once again, it's important to understand the math and what does it mean. Otherwise, you only know how to form formulas and know how to plug in numbers to get some other numbers, and that's really not that exciting. Okay? So what does this actually divergence mean? So how about we calculate a number and then we can see what the implication of it is. So I'm going to look at this picture right here and maybe pick a number that we can calculate. So maybe we pick the number 3, for instance. Maybe we'll pick a point right here, 3, 1. Okay, let's see if we can label this point. So 3, 1 is somewhere, maybe somewhere over here. Oops. Okay, that's the point 3, 1. So let's calculate this value and see what happened. So at the point 3, 1, the divergence of f would equal to 2 times x, which is 3, that equal to 6. So now we have a number. What does it mean? This is what it means. When the number is greater than 0, positive number, that means divergence of f is positive. Then what does that tell me is that the neighborhood tend to expand. And therefore, in this case, flow lines diverge from each other. And with the magnitude of the numbers, meaning in this case 6, indicate how quickly they diverge from each other. With the larger value probably telling me that they diverge faster. Or you can see that the way they move away from each other is more dramatic. While versus a slightly positive number would be less dramatic. So important to understand is that when the divergence is positive, the neighborhood is expanding, and therefore the lines are diverging from each other, which kind of makes sense because it is called divergence. And if you look at the picture, you can also see that it's being true, as in this point, the flow line will probably be moving away from each other as they loop around to the other side. So now come the interesting question is, what happens when we pick a point over on this side? Maybe negative 3, positive 1. And what happened to this point over here? And for some of you, you can probably already guess that it's going to give a negative value because it's actually contracting, converging. So, on the flip side, at negative 3, 1, the divergence of f is equal to 2 times negative 3, which is negative 6, which is less than 0. So what does that mean? What does that mean is, actually, I kind of wrote it. All right, there you go. That would imply that the divergence of f at that point is negative. And therefore, the neighborhood tend to contract. And therefore, flow line can be seen to converge toward each other. So, in this case, when the divergence is negative, the neighborhood contract, and you're actually converging instead of diverging. Now, so that's not too exciting. So maybe we'll try another example, and we're going to try to calculate the divergence and see how that works out. Now let's try another example on calculating divergence. So how about let's do this picture right here. How about let's say we're going to give you vector f of xy equal to, how about just equal to xy? I'm going to ask you to find the divergence of f. So remember, in this case, f map from R2 to R2. So therefore, the divergence of f would only just be df1 over dx plus df2 over dy, which in this case is d over dx of x plus d over dy of y. And so in this case, it actually just come out to be 1 plus 1, which is 2. Now, notice in this case that the divergence of f is equal to 2, which is a constant. So now the interesting question I want you to think about is what does that mean about the flow line of this vector field? So try to think of it this way. Because the divergence is a positive number, therefore indicate that the neighborhood tend to expand near a point. And because the value is a constant, regardless of where you are, you can kind of anticipate that the flow line kind of expand or move away from each other at the same fixed rate. So let's show you what this vector field look like, and then you'll see that it will kind of make sense. So this is this one right here. Okay, once again, I don't know where it pop up. Oh, right here. Oh, that doesn't look too good. Yeah, that doesn't look good either. I'm going to have to undo. Okay, there you go. I'm going to try to drag it out this way. Yeah, there you go. Now much better. So now look at this vector field xy. Notice that all the flow lines, actually kind of radiate out from the center. Like this. And so all these flow lines actually kind of just continue to diverge from each other from a single point, and therefore you can see that they actually kind of have the same rate of how it's spread from each other. And that's what would happen when you have a fixed divergence. Now, maybe give you one last example to illustrate, and then that would be it for today. So what happened to this one? How about vector f of xy is equal to x plus y, y? Notice that the divergence of f is equal to d over dx of x plus y plus d over dy of y. And that come out to be 1 plus 1 equal to 2 also. But does that mean that this one behaves the same way as this one? No, because the vector field is different. But the flow line behave the same way. So now the question then is how this field look like, and how the vector, how the divergence of it show how the flow line behaves. So let's see. So once again, I don't know where it's going to pop up. Oh, there you go, right here. So notice that this one, the vector field actually have flow line that curve. But the idea is that as they curve away from each other, it kind of maintain how far apart they are by gradually growing at a constant rate. So you can see that like the flow line, as you draw them, they would gradually diverge from each other, and the way they diverge is kind of maintain the same magnitude, which is in this case 2. Different compared to this picture, where the divergence will be changing at each point. As you can see, maybe in the beginning, it divergence is bigger, but then as you move backward, the divergence is smaller, so that the flow line kind of flow not as far away from each other or expand in the same rate until they eventually converge back toward each other. So hopefully the concept of divergence kind of makes sense. It's basically just trying to show you when you draw two flow lines, are they floating away from each other or toward each other? And that is dictated by whether the divergence is positive or negative while you're drawing it. And remember, the divergence is position dependent, so it tend to dependent on the position x and y. But in some cases, if it does have a constant divergence, that just means that the way the flow line are separate or move away from each other or move towards each other maintain kind of the same behavior throughout. All right. Unfortunately, I think we're going to stop right here instead of talk about the next concept. We're just going to do it on the next video. All right. And I'm going to end right here, and I'll talk to you guys again in the next video. Okay, bye bye.